Alright, so now that we understand the concept behind and the intuition behind the notion of a derivative, let's go ahead and compute some. So using the limit definition of the derivative, we're going to go ahead and compute some derivatives. So our first question asks, the derivative of f of x equals 2x squared minus 16x plus 35 using the limit definition of the derivative. So we know that the limit definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, to compute our f of x plus h, all we need to do is just substitute an x plus h wherever we see an x in this original function. So I'm going to write it off to the side here. So our f of x plus h is going to be equal to, wherever we see an x in here, we're going to substitute an x plus h. So it's going to be 2 times the quantity x plus h squared minus 16 times x plus h plus 35. Now I'm going to go ahead and distribute all of these terms and FOIL out things. So just to make it simplified and just separate terms instead of having these multiplications that I have to worry about. So the first thing I'm going to do is I'm going to FOIL out this x plus h. So if I go over to the side here, x plus h, x plus h. So this is the same thing as saying x plus h quantity squared because I'm multiplying two x plus h's together. So if we FOIL this, our first terms together is going to be x squared. Our outer terms together are going to be xh. And our inner terms are going to be xh again. And our last terms are going to be h squared. So this is going to be x squared plus 2xh plus h squared. So if I go over here to our f of x plus h function, we still have this 2, and now we FOILed this x plus h out, so we can write this in substitution for that. So we're going to have x squared plus 2xh plus h squared, and then I'm going to go ahead and distribute this minus 16. So if we distribute the minus 16 to the x, we get minus 16x. If we distribute it to the h, we get minus 16h. And then we have this plus 35 at the end. Now I'm going to go ahead and distribute this 2 to all these terms. So we have 2 times x squared, which is going to be 2x squared. 2 times 2xh is going to be 4xh. And 2 times h squared is going to be 2h squared. And we're still going to have all this stuff at the end. Alright, so now that we have our fully simplified f of x plus h function, don't want to erase that. So our fully simplified f of x plus h function, we're going to go ahead and substitute that into our limit. So this is going to be, now that we've simplified things, the limit as h approaches 0 of f of x plus h is now this, so we're going to substitute that in. So we have 2x squared plus 4xh plus 2h squared minus 16x minus 16h plus 35. And we're going to subtract away our original function f of x. So all we have to do is just put a minus sign, and make sure you include a bracket here. Don't just do minus and then this function. You're minusing the whole quantity. So you have to make sure that you have the parentheses. And then we're going to plug in our original f of x. So that's going to be 2x squared minus 16x plus 35. And all of this is going to be over h. And I'll erase this f of x plus h because we don't really need it anymore. So now that we have this limit, it looks pretty complicated, but we're going to try to simplify this out and cancel some terms. So the first thing I'm going to do is I'm going to distribute this minus to all of these numbers over there. So I'll be left with a limit as h approaches 0 of 2x squared plus 4xh plus 2h squared minus 16x minus 16h plus 35. Since we're distributing this minus, it's going to be a minus 2x squared. Minus times negative 16x is plus 16x. And a negative times a positive is going to be a minus 35. And this is all going to be over h. Now, if you notice, we can begin to cancel out some terms. So we have this positive 2x squared. That's going to cancel out with this negative 2x squared we have over here. We have a minus 16x. That's going to cancel out with a plus 16x we have over here. We have a plus 35. That's going to cancel with a minus 35 that we have over here. And that's pretty much all we can cancel. So with all our terms canceled out, or not all of them, but most of them, we can write this limit as the limit as h approaches 0 of 4xh plus 2h squared minus 16h, and this is all over h. Now the whole reason why we couldn't even compute this limit in the first place was because if we substituted in h equals 0, we would have a 0 over 0, which would not be beneficial to us. So what we have to do is we have to try to cancel out this h somehow. So the way we can do that is out of this numerator, you can notice that all of these terms have an h in them. If we can factor out that h, we can cancel it with the denominator, and then we can just substitute in our h without a denominator, and we won't have to worry about anything. So let's go ahead and do that. So if we factor out an h out of our numerator, we get h times 4x plus 2h minus 16, and then this is all going to be over h. Now we can easily cancel out these h's. So this h goes away, this h goes away, and we're left with the limit as h approaches 0 of 4x plus 2h minus 16. Now it's just an easy substitution. So this is going to be 4x plus, wherever we see an h, we're going to substitute in a 0. So 2 times 0 minus 16. Make sure you don't substitute a 0 in for where there's an x, because it's not the limit as x approaches 0, it's the limit as h approaches 0. So be careful about that. So now that we have that, this 2 times 0 is going to go away. That's going to be a 0. So we're going to be left with 4x minus 16. And that's going to be our derivative of 2x squared minus 16x plus 35. Now, to understand what this means, remember in the last video I said that the derivative is just the slope of the tangent lines of the graph at any given point. So this is not really a scalar. This is not just a regular constant, how we usually write slope. This is a function. So what this function is telling us is on the graph of f of x equals 2x squared minus 16x plus 35, which would probably look something like this. Let's say that we wanted to find the slope of this graph at the point x equals 2. So if that was the case, we would plug 2 into our derivative, so that would be 4 times 2 minus 16, which would give us 8 minus 16, which is negative 8. So at the point x equals 2 on our graph, if we drew a tangent line to that point, our slope of that tangent line would be negative 8. That's what this function is telling us. So now that we understand what that means, we can write the formal answer. So whenever we're saying that the derivative of a function is equal to another function, we use prime notation. So we would say that f prime of x, which means the derivative of f with respect to x, is equal to 4x minus 16. Now, sometimes you'll see it written as this, d dx f of x equals 4x minus 16. These basically mean the same thing. D dx is just a derivative operator. That means you're taking the derivative of the function inside. But usually when we're writing a final answer, we use this prime notation. All right, so now let's move on to our next example. So we want to find the derivative of g of t equals t over t plus 1. So going back to our limit definition, we have the limit as h approaches 0 of g of t plus h, because now we're using t as our x value and g as our f. So this is going to be g of t plus h minus g of t, and this is all going to be over h. So now we need to find out what our g of t plus h is going to be. So we can write g of t plus h on the side here. So now we're just going to plug in wherever we see a t in our original function, we're going to plug in a t plus h. So our numerator is going to turn into t plus h. Our denominator is going to turn into t plus h plus 1. This was originally a t, and this was also originally a t. So we just plugged in a t plus h. All right. So now that we have that, we can go ahead and substitute it into our limit. So this limit is going to be the limit as h approaches 0 of our g of t plus h function, which we have right here. So g of t plus h is t plus h over t plus h plus 1. And we're going to subtract our original g of t, which is t over t plus 1. And this is all going to be over h. Now we have a complex fraction. We can go ahead and combine these two, and then divide it by h. So off to the side here, I'm going to combine these two fractions. So we'll have t plus h over t plus h plus 1 minus t over t plus 1. Now to get our common denominator, we're going to have to multiply this fraction by the denominator over here and this fraction by the denominator over here. So let's go ahead and do that. So this is going to be the same thing as we're going to multiply this fraction by t plus 1. So we're going to have t plus h times t plus 1. And our denominator is also going to be t plus h plus 1 times t plus 1. And then this left fraction, we're going to multiply everything by t plus h plus 1. So we're going to have t times t plus h plus 1 over t plus h plus 1 times t plus 1. So now we have a common denominator. We can combine these fractions. So we have t plus h times t plus 1 minus, I'm going to make some space here, minus t times t plus h plus 1 all over t plus h plus 1 times t plus 1. Now we can go ahead and FOIL things out on the numerator and distribute things. So our t plus h times t plus 1, if we go ahead and FOIL that over here, our first terms are going to be t squared, so t squared. Our outer is going to be t times 1, so plus t. Our inner is going to be h times t, so plus ht. And our outer is going to be h times 1, so just h. Or plus h, there we go. So we can substitute that back in, so we have t squared plus t plus ht plus h, and then we're going to distribute this minus t to all these terms. So we're going to have a minus t squared minus ht minus t. All of this is going to be over t plus h plus 1 times t plus 1. Now we can cancel out some terms. So we can see that we have a positive t squared over here. That cancels out with a minus t squared right here. We have a plus ht, which is going to cancel out with a minus ht. And we have a plus t that's going to cancel out with a minus t. So we're going to have h minus, or sorry, nothing else on the numerator, so just an h. And on the denominator, we're going to have a t plus h plus 1 over t plus 1. And this fraction right here is going to be equal to this numerator. So we can substitute it back into our limit by saying the limit as h approaches 0 of, in our numerator, we're going to have this fraction. So h over t plus h plus 1 times t plus 1. And this fraction is going to be over h. Now, we need to simplify this complex fraction. So the way we do that is we're dividing this fraction by h. So that's basically the same thing as multiplying by 1 over h. So all we have to do is just move this h to this denominator right here. So we can write this limit as the limit as h approaches 0 of h over h times t plus h plus 1 times t plus 1. Now, our problem of a 0 being on the denominator is gone because we can cancel out these h's. So now, we have the limit as h approaches 0 of 1 over t plus h plus 1 times t plus 1. If we substitute in a 0 wherever we see an h in this denominator, we have 1 over t plus 0 plus 1 times t plus 1. Remember, again, don't substitute in a 0 wherever you see a t because it's not the limit as t approaches 0, it's the limit as h approaches 0. So we only had one h we had to substitute in with a 0. So now we can simplify this. This is 1 over t plus 1 times t plus 1, or 1 over t plus 1 quantity squared. And that's our derivative of g of t. And again, to reiterate what this means, if we plugged in t equals 2 to our derivative at the point t comma, or 2 comma g of 2 on our original graph, our derivative evaluated at t equals 2 would be the slope of the tangent line there. Now, we're going to do one more example, and I'll let you guys try it on your own, and then come back when you're ready to see the full worked out solution. So go ahead and give this one a try, and come back when you're ready to see the solution. Alright, so hopefully you gave this problem a try. So again, we're just going to start off with our limit definition. So we're going to have the limit as h approaches 0 of, in this case, r of z plus h minus r of z all over h. Now, we need to find out what our r of z plus h is going to be. So our r of z plus h is going to just be equal to, wherever we see a z in this function, we're going to plug in a z plus h. So we're going to have the square root of 5 times, there's a z right there, so we're going to plug in a z plus h. So quantity z plus h, and then we have just a minus 8. So going back to our limit, we have the limit as h approaches 0 of r of z plus h, which we can substitute in. And then we're going to subtract away our original r of z, which is the square root of 5z minus 8. And this is all going to be over h. Now, I'm going to delete this r of z plus h over here. So we can, it's not really obvious how we can, compute this limit, because there's not really a way we would be able to cancel out this h. So what we have to do is we have to multiply by the conjugate. So remember, multiplying by the conjugate is when you're given a fraction a plus b over some constant or something, or any other function really, you multiply the top and the bottom by a minus b, and that allows you to cancel out some terms. So let's go ahead and do that. So in this case, our a is going to be this over here, and our b is going to be this over here. So we're subtracting them. So we're going to multiply by the sum of them. So on the top, we're going to multiply by 5 times z plus h minus 8, the square root of 5 times z plus h minus 8, plus the square root of 5z minus 8. And we're going to do that for the same thing on the denominator. Okay. And now, well, the reason why we can do this is because if you divided this out, we have the same thing on the numerator and the same thing on the denominator. So this is the same thing as multiplying by 1, but the only reason we do this is because it allows us to cancel out terms. So let's go ahead and see how it does that. So we have the limit as h approaches 0 of this is one term, and this is going to be another term. So all we have to do is FOIL this out. So our first terms multiplied together is going to be these two multiplied together. So we have the square root of something times the square root of the same thing. So that's just going to give us that thing that we have under the square root. So we have 5 times z plus h minus 8. And then our outer terms and inner terms are going to cancel because we have this times this. But then we also subtract this times this. So we're adding the same thing and subtracting the same thing. So that's just going to give us 0. So we don't even need to compute that. And now we're going to multiply our last terms together. And again, the same thing happens. We have this minus sign because we're doing a negative times a positive. And then we're multiplying the square roots of the same thing. So that's just going to give us the thing that's under the square root. So we're just going to be having a 4z minus 8. And this is all going to be over h times this term right here. So this is all going to be over h times the square root of 5 times z plus h minus 8 plus the square root of 5z minus 8. Now we can go ahead and distribute terms up on the numerator and cancel things out. So we have the limit as h approaches 0 of 5z plus 5h minus 8 minus 5z plus 8 all over h times the square root of 5 times z plus h minus 8 plus the square root of 5z minus 8. Now we can go ahead and cancel some terms. So in the numerator, we have a positive 5z. That cancels out with a negative 5z we have over here. We have a minus 8 that will also cancel out with a plus 8 we have over here. So we're just left with the limit as h approaches 0 of 5h over this denominator plus the square root of 5z minus 8. And now we can cancel out these h's. So cancel this out, cancel this out. We have phi. Okay, so we've canceled out these terms. So now I'll scroll down. And then we have the limit as h goes to 0 of 5 over this quantity. So the square root of 5 times z plus h minus 8 plus the square root of 5z minus 8. And now wherever we see an h, we're going to substitute in a 0. So we're going to have 5 over the square root of 5 times z minus 8 plus the square root of 5z minus 8. And these two, if you notice, are the same thing. So this is just the same thing as saying 5 over 2 times the square root of 5z minus 8. And this is going to be equal to, our original function was called r of z, so our derivative is going to be called r prime of z. So r prime of z is equal to 5 over 2 times the square root of 5z minus 8. And we are done.